Okay, let's resume. So again, here we have the central question. The central question is difficult. Why is it interesting? So I'm gonna give you maybe two ways of answering the why is this interesting question. The first way is to make an analogy to other kinds of metric spaces where something like this question is true. The second way to answer this question is to give you applications, where if it is true, it means we can prove other theorems. So let me take you to a slightly different world. Okay. So I'll say like reason reasons to believe the answer to the question is yes. Okay. So the sort of motivation here is to think about hyperbolic geometry. Okay. So we're gonna start with um, a surface S. Let's say, let's just to make things simple, okay, orientable, closed, genus, at least two, just to avoid some degenerate simple cases. Okay. Then then there exists a complete finite area Riemannian metric of constant curvature, sectional curvature -1. Okay, this is a hyperbolic metric. Okay, and there's many ways to think about this. Okay, like if you're sort of more algebraically minded, like I can tend to be, maybe you want to think about this as, another way to think about this is, there exists an injective homomorphism, let's say rho, from the fundamental group of the surface into the orientation preserving isometries of the hyperbolic plane, whose image is discrete. So this is a more sort of like Lie group theoretic geometric structure way to say this, as opposed to a more like Riemannian geometry way to say this. Okay, and so what this means is, you have some um, map that takes every element of the fundamental group into the group of isometries of the hyperbolic space. And this word discrete just means that if I take the orbit of any point in the hyperbolic plane, which I'll think of as being the Poincaré disk. So I pick some base point x and I take all of its images under um, the maps that lie in the image of rho, then I don't see any accumulation points on the interior of the disk. I only see accumulation at the boundary. And so these are precisely the requirements that you would need to be able to say that if I take H2 and I quotient out by the action of this subgroup of isometries, then what you obtain topologically is the surface that you started with, and um, this quotient um, gives rise to the Riemannian metric of constant curvature -1 on the surface. So there's two ways to think about it. Okay. Now, there's a very fundamentally important and basic lemma in hyperbolic geometry in this setting, and it's called the Bers lemma. And here's what it says. It says that there exists a constant, let's call it L. Here, L depends only on the genus, not on the actual, uh, not on the row. I mean, so first of all, if you go back to this page, I mean, I apologize to anyone for whom this is obvious. I don't know what the backgrounds are, so I'm trying to go as slow as possible. But on this page, I just say there exists. But of course, like if you know this world, it's way more than there exists. There's an entire uncountably infinite moduli space of different choices you could have for such an injective homomorphism, or if you want to think about it Riemannian geometry wise, such a metric that's up to isometry. So there's this entire multi-dimensional space of choices. This is what's referred to, depending on how you want to think about it, as either the Teichmüller space of the surface or the moduli space of hyperbolic metrics. Depends on the language you're using. And so there's many, 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 many choices. And so I want to emphasize that the lemma I'm about to state depends on none of those choices. It only depends on the genus, not on the particular metric that you choose. Anyway, what is this constant? Uh, the constant is the following. There exists a constant L so that there is at least one closed geodesic on S of length at most that constant. Okay, so it's impossible to have a hyperbolic surface of a fixed genus where every closed geodesic is extraordinarily long. That can never happen. Now, what's the proof of this? The proof of this is very simple, actually. It relies on the Gauss-Bonnet theorem from classical Riemannian geometry. Okay, the Gauss-Bonnet theorem applied to triangles in the hyperbolic plane immediately tells you that the area of a hyperbolic triangle where the interior angles are beta, alpha, and gamma is pi minus the sum of those angles. Okay. Now you can use this very basic fact to argue. So this is maybe step one, is just the first is Gauss-Bonnet. Step two is use step one to argue that, in fact, I don't even need to say it like this. I'm making things overly complicated for no reason. Let me just rephrase this because I can just apply Gauss-Bonnet directly to the hyperbolic surface. So ignore this and let me rewrite this. What does Gauss-Bonnet say? Gauss-Bonnet, it says that um, if I take the integral of the curvature over my surface, then this has to be equal to like 2 pi times the Euler characteristic of the surface. Okay. Now, the I don't know why I wrote D here. This should have been S. Okay. This is what Gauss-Bonnet says. Now, what is the curvature? The curvature is minus 1. This is minus 1. And so what this tells you is that this implies immediately that the area of S is is equal. Oh, there shouldn't have been absolute value signs there. This is the Gauss-Bonnet theorem. So the area of S has to be equal to 2 pi times the absolute value of the Euler characteristic. And this is a topological invariant. It doesn't depend on anything except the genus. The genus here, of course, determines the topology by the classification of closed orientable surfaces. So the point is that the area of the surface only depends on the topology of the surface and not on the choice of metric. So why is this relevant to proving the Bers lemma? Because what you can do now is you can do the following thing. This is step one. Step one is just observing that Gauss-Bonnet implies that the area of our surface is some constant that depends only on the topology. Now, step two is to say, okay, let's just imagine inflating a metric disk on S. So you can start like with a single point and then imagine a movie where you start growing a ball around that point, larger and larger and larger. Okay. And then it gets like, and these are all metric disks. So these are just actual balls in the hyperbolic metric. Okay. Now the fact that the area of S equals 2 pi chi of S implies that before long, this ball cannot be embedded on the surface because otherwise there would be too much area on the surface. Okay? The area of a hyperbolic ball, the area of a disk of radius, I don't know, r is I who knows the exact formula? I forget, but it's like something exponential in r. It's like some kind of a cosh function, cosh of r, something like that. Okay? It depends exponentially on R, but whatever. There's some formula you can look up. Okay. So since the area of S is 2 pi chi of S, it implies that any ball of radius uh, much bigger than the log of chi of S is not embedded. And that means that if I take such a ball, then it has to sort of wrap around the surface in some way, right? Like it has to kind of like hit itself. There has to be a point of tangency here eventually. And it's not hard to prove topologically that this loop I just drew is homotopically essential. And therefore, it has a geodesic representative. And that geodesic representative will have length at most the length of this loop, which is at most the diameter of this ball. So that's the very rough outline of how to prove the Bers lemma. Okay. I'm being vague here. I'm not being as formal as possible, but that's okay. We're just speaking here. Okay, so now, why is the Bears lemma relevant to anything we're talking about? Okay, well, here's another fact. Here's another, let's say, basic lemma in hyperbolic geometry. Okay, well, in fact, let me state this a little bit more carefully. So I'll call this an actual. This is a theorem, and this is a theorem that is due to Hubert from the 50s. Um, Generalized greatly by Margulis in his thesis. Okay, so the theorem is as follows. You can define the entropy of one of these surfaces, and in fact, any metric space in the exact same way that we defined it for metric graphs. Okay, it's just you can define it in this following way, right? H of S, where now S is a hyperbolic surface, is just the limit as L goes to infinity of the number of um, the number of uh, closed geodesics, number of closed geodesics on S with length less than or equal to L, and I take a logarithm of this, and I divide this by L, and this is a fabulous result. The result is that this limit not only exists, but it doesn't depend on either the metric or the topology. It's actually always one. This is a miracle of hyperbolic geometry. Okay, this goes back to the 1950s. Okay, well, one can use this theorem to prove the following lemma. Um, uh, Let S be a hyperbolic surface. Now I'm going to relax one of the assumptions on the surface. Up until now, our surfaces have been, if you remember from the very beginning, closed, which means no boundary. So our surfaces look something like this, topologically speaking. Okay. But now in this lemma, I'm going to allow boundary. So let S be a hyperbolic surface with a totally geodesic boundary. So maybe it looks like this now. Okay. Then there exists a Bers constant for S depending only on the length of the boundary. So a Bers constant here, what I mean is, what do I mean when I say that? I just mean um, that there exists some L so that there exists a closed geodesic within S, so not the boundary, of length at most that number. So there's some upper bound that captures the length of the shortest closed geodesic. Now, why why doesn't, let's just make sure we understand. Why doesn't the same argument we use to prove the Bear's lemma in the closed case work straight away without any revisions once we add boundary? It's because if you start to inflate a metric disk inside of a hyperbolic surface with boundary, it may hit the boundary before it achieves its full area. And so you have to be more cautious. And it turns out that the result that you're able to obtain is a similar result, but it may depend on the length of that boundary component. If the boundary component is very, 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 very long, then the L might get very long. Okay. Any questions about this before I start to examine why this is related to anything we're talking about? Okay. So finally, what I'll just say is that um, uh, another lemma that I won't prove, but that I hope is believable to you, is that the entropy of a surface is related to its Beer's constant. So in other words, um, small Bers constant implies large entropy. In other words, if you can find even one closed geodesic with length under a small bound, then you can use very basic topology, hyperbolic geometry to argue that in fact you can find many. And so if the Bayes constant is small, the entropy has to be bounded from below. So um, let's now put all of these facts together to prove a theorem. There exists lambda bigger than zero, where lambda here depends only on the genus, the topology of the surface, nothing else. So that if S is any closed hyperbolic surface, then there exists a proper subsurface. Let's call it H with entropy bigger than lambda. I hope this reminds you of something. This is precisely the central question in graphs that we started the talk with a while back, except now it's for hyperbolic surfaces and hyperbolic subsurfaces. And the proof of this theorem is now quite straightforward. The proof is first you use the Bayes lemma, and that tells you that there exists a closed geodesic on S with length at most some number that depends only on the genus. Okay? Then you just cut along that geodesic. And this gives you a subsurface H with totally geodesic boundary. So the picture here is here we have some original surface. We're guaranteed to find some geodesic with length at most L. Now we're going to cut along that geodesic and we get some surface that looks like this. Okay, where the total length of the boundary is like, I don't know, 2L, right? Because each of these has length L or something. So now um, uh, we just apply this final lemma here, which says that I can get a lower bound on entropy when I have a small Bayes constant. Okay, and and what this what sorry, there's one other lemma from here that we also stated, which is that when you have a surface with totally geodesic boundary, there is a Bayes constant for L whose size depends only on the length of your boundary, right? So now coming back here, we say that there exists some not too long closed geodesic. We're calling this H on H. Maybe it's here. And then we use the final lemma to say that the entropy of H is not too small. And that's the sketch. That's the proof. Okay. So all of this comes together to prove this theorem in
Uh,
hyperbolic geometry, and it's the precise statement that we're trying to address in the setting of metric graphs.
Sorry, Tarik. I, I,
Yes.
I have a question. So, what is your definition of of entropy in the case of surfaces of with a boundary?
In the case of a surface with boundary,
Yeah, because
yes.
if there is no boundary, the entropy is one. Yeah.
The entropy is one, exactly. Now, in the event of a surface with boundary, it's the same definition. The definition is just counting the number of closed geodesics on this surface with a totally geodesic boundary.
Mhm.
Now you take the logarithm of this count, divide by L, and take a limit. The entropy is not one, but it is something.
Less than one? Oh no.
Less than one. It's going to be
Fine.
less than
Okay.
one,
Okay.
exactly.
Okay. Okay.
Okay, so yeah, right. So now, what this tells us is that our central question in graphs, it is true in other settings, except in those other settings, one has access to way more structure than one has in a graph. Like the key to proving this statement in hyperbolic geometry is the rigidity of hyperbolic geometry. The Gauss-Bonnet theorem, the fact that every hyperbolic surface has the same area, the fact that every hyperbolic surface which is closed has the same entropy equal to one, and entropy and area are related in this fashion. All of this dies in the setting of graphs. So if we are to prove the answer is yes for graphs, we need new tools. But at the very least, this analysis suggests that the question is motivated. In the last maybe 10 minutes, I want to tell you one final reason why this question is interesting. Um, First of all, now it's motivated, but also it has applications if the answer is yes. So, applications for the central question. Okay, so there's this whole beautiful classical theory of Teichmuller theory and moduli spaces of hyperbolic structures on surfaces, and it's a very long and beautiful story, and I don't have time to get into all of the technology and details there. But I'm just going to say that one can very naively define a moduli space of metrics on a graph without any technology. Uh, and so here's what one does. So fixing a graph G, here's our graph. Who knows what it looks like? Okay. No metric yet. Then it's easy to see that the set of all possible metrics, all metrics on G corresponds basically with some piece of Euclidean space where the dimension is the number of edges, and we're only looking at the sort of positive quadrant or octant of this Euclidean space because we require that we assign each edge a positive length. If I hand you a metric on G, it's equivalent to handing you a positive weight to each edge, and so one obtains this identification. Okay. So this is not a very interesting identification. It's sort of obvious, right? But w one of the reasons for studying hyperbolic geometry, I'll just say it like this, algebraically, one does Teichmuller theory to understand the mapping class group of a surface So if you don't know much about this, I'm happy to answer questions about it, but I think it would just take us too far afield for me to get into the details, and we don't have much time. I'll just say it is a centrally important group that is studied in surface topology, in three-manifold topology, and four-manifold topology. And the sort of point of geometric group theory is to study the algebra of a group via a geometric action that it enjoys on some space that you have access to. So the Teichmuller space, the space of hyperbolic metrics on a fixed surface, admits a very beautiful action of this group. And through the geometry of the space, there's information that is encoded about the algebra of the group. And so this is one of the motivations for doing Teichmuller theory. Now, there is a much larger, much less well understood group that people are now very interested in understanding, trying to buttress the tools that they've developed in the setting of mapping class groups to this more wild setting. And this is the group which is called the outer automorphism group of the free group. Okay, so out Fn is a much larger group, which there's a relationship between the mapping class group and the outer automorphism group of the free group. One sort of, if you think about it in the right way, sits inside of the other. Okay, and so the outer automorphism group is much larger, much less well behaved, and much harder to control. But the analogy is as follows: out Fn is to some analog of the Teichmuller space that we've yet to define. So I'll put question marks here. Like, what should this be as the mapping class group is to Teichmuller space? And it turns out that the most natural object to place inside of these parentheses has a name. It's called the Kohler-Voigtman outer space. And the idea for this outer space is not it's not too complicated. It's really not. Um, in fact, um, it's sort of it's very much related to this. I mean, the idea for outer space is you have for a given type of for a given rank, as we discussed in the first part of this talk, there's only a finite number of different graphs of that rank, right? Like maybe there's this one, there's a few other kinds, right? Every rank only has a finite number of topological types, and each rank is related to a chunk of Euclidean space via this identification. And now you get the outer space by just gluing these cells together in the appropriate way. And you glue these cells together in exactly the way that you'd be required to do in order to obtain a well-defined action of this particular group on the space. So all of this is like sweeping huge details under the rug. I'm not giving you much detail, but I'm just trying to convince you that there's relationships here to some deep mathematics. Okay. So now we have some space that is the analog of the Teichmuller space in the setting of this much larger group. But if you want to do geometric group theory, you don't just need a space, you need a metric. You need some kind of geometry on that space in order to leverage the geometry to tell you something about the algebra of the group. So now one needs to consider possible metrics. How do we metrize this outer space? And there's a beautiful set of ideas coming from thermodynamics, actually, which give a candidate for a metric. And this comes from work of Polycott and Sharp, and there's other people involved as well. But I'll just say that there exists a metric on the outer space that is the analog of a very, very well-known metric in the Teichmuller space, which is called the Weil-Petersson metric. Okay. And Polycott and Sharp define this metric. They don't study too many of its properties. Their paper is mainly focused on showing the well-definedness of this metric. And it's not straightforward. Because again, I'll just say like the way the Weil-Petersson metric is defined classically in the setting of surface topology is through complex analysis. It uses the fact that um, the set of it uses the uniformization theorem in complex analysis, which says that to every conformal class there is a unique constant curvature metric of curvature minus one, and so there's no difference between the complex analytic framework and the hyperbolic geometry framework. And so you use this connection to complex analysis to define this metric. In graphs, there is no complex analysis. You don't have any complex structure on a graph. And so they have to think hard about how to make this work in the setting of graphs. But I'll just end because we are running out of time, I think, by saying what the application is. So application to central question being true is we can prove diameter bounds on this metric if we know the question, if we know the answer to the question is yes. And so finally, after 90 minutes, I'll just state our theorem. This is again joint with uh, Tarik Ahmed and Matt Clay. And the theorem is that the answer is yes. Okay. So we are able to prove that there is a proper subgraph of any metric graph of entropy 1 with definite entropy. The techniques, which unfortunately I wasn't able to tell you much about, go through what's called the Gibbs state, which is a sort of tool in dynamics that allows you to basically use some linear algebra alongside some basically like a graph theoretic analog of thinking about the geodesic flow on a hyperbolic surface. We analyze this Gibbs measure and we are able to do some reductions in the graph, some inductive arguments to obtain the result. I can say more if there are specific questions about our techniques, which again, I wasn't able to get into very much of. But I hope at the very least, I told you about a question. I told you why the question is motivated and why it's hard, and I told you the answer to the question. Thanks for your time and your attention.